Hello again, folks, in 114. Today we'll be covering sections 12.2. Almost said 7 for some reason. Not quite awake yet. Okay. Hopefully I'll become a little bit more focused. 12.2. Because today is Tuesday, June 22nd, so 12.2 is on the agenda. Okay? The packet that I have for you today consists of quite a lot of stuff, actually. There's firstly this overview of different diagrams. I'll go through this and you can annotate if you'd like. There's some terminology, so I added another one of these blank tables that I like to for some vocabulary. Then there are examples of my own choosing. Some of these are taken from another book. We'll go through that. A diagram for 2 of these. That was blank. Just a scaffold. There's some procedures that I swiped from your book, just in case you prefer. They're pretty good, actually. They're concise, right? But I promise you, I will not leave you stranded. There's some information about histograms and some formulas. Okay. This is just again some scaffolding if you're going to draw a histogram from scratch. I made this sheet, and then there's some the same formulas that I had taken from your textbook. Basically, I put here just for the sake of comparison and contrast. And this is about stem and leaf plots. So there's naturally a stem and leaf diagram. And then I'll walk you through how you might make a pie chart if you'd like. I don't have an audience, unfortunately, so the best I can do is basically give you some survey data from a couple of semesters ago, but I'll show you how you could make a pie chart, either via Excel or just doing it brute force, which is, I think if you do it by hand, it actually is very satisfying. And I'll show you the intricacies of it. All right, you appreciate what Excel does a little bit more. Let me turn on the projector here. And adjust the lights. That may be a little too dim. Let's see. Put this aside. Okay. Let me show you this overview. To give you an idea. Well, let me start with this perhaps. Here's the diagram just to give you some structure for the chapter 12 in general. All right. Last time we had covered the royal we. This was gathering and organizing data. This was section 12.1, and today we're going to be talking about the actual presentation of data. So essentially, if you had to make a diagram or a chart of some sort, all right, this is 12.2, where we're at right now. Okay. With that in mind, take a look at this overview, unique to the section, and I'll explain the details of this. Okay. All right. Now, let me start with this. You might have heard an expression, array, especially if you've taken some kind of a programming class. A lot of times they talk about arrays. A data array is basically organized to the extent of it being in whatever your data is. All right. It's sort of in a rectangular table. All right. So what you see here, this is vitamins A and B and C and D, all right, just kind of jumbled, right? Not particularly organized, but it's in a rectangular sort of regimentation here. And if you have something at least prepared that way, truly a table, this is rectangular, right? This is best referred to as an array. What you do in the long run is you take your array of data collected and then attempt to present it in a way that is palatable to the general public, right? So that's really what the whole section of this that the topic of this section is about. Taking something that's jumbled, partially organized at best, and presenting it in a way that it is palatable and understandable and appreciable to other people. Right? So, what choices do you have? Well, the kind of things that we have to talk about in this class are first and foremost frequency distributions, right? And there's basically two types. There's categorical frequency distributions, and then there's grouped, or what you might call continuous frequency distributions, all right? Essentially, these are bar charts, all right? But there's some distinction between the two of them, you'll see in a moment. Another alternative is what you might refer to as a stem and leaf plot. Right? The benefit of doing something like this, although it's very similar to a grouped frequency distribution, is that you get to actually see the numerical data. Right? Bar charts kind of, obscure it. It just presents information as different height bars. All right, but you actually see the actual numerical values, and they kind of look like something like a bar chart on its side. All right. More often than not in media, all right, when you see any sort of data given to the public for digestion, all right, it's in the form of a pie chart. All right, so you have sort of rectangles, you have sort of sideways rectangles, and you have circles. All right. Now, what do these do? All right. Frequency distributions that are the categorical type are gapped. All right. They're distinct bars. All right. These are very distinct bar charts or bar graphs. Right? They're categories that are not related to one another, they just coincide. All right? Grouped or continuous frequency distributions basically offer a continuum of what they call is classes. Right? The data is related somehow, but there's bar charts basically illustrate where the frequency most occurs. All right. Anyhow, make this distinction. If you have a categorical distribution, your bars are gapped. All right. If you have grouped or continuous frequency distributions, these are not gapped. Right. They have to be one continuously butted up against another. All right. A sort of lump, if you will. All right. These are referred to, when you get into this category, not simply referred to as bar charts anymore. The preferred term is histogram. They are visually a glorified bar chart, but again, because they're not gapped, we refer to them, the royal we, as a histogram. Okay. Now, similarly, before I move this down, a stem and leaf diagram, all right, is very much like a histogram. That is a bar chart, sort of, all right. But instead of it being vertical, these are vertical bars. You can imagine that these would be sort of sideways or horizontal bars. People tend not to draw the bars around the data, but they could. All right. So it really is just a sort of a grouped continuum. But it's just written sideways. All right. Again, the advantage of having a stem and leaf diagram is that you actually see the data. You can view it. It's preserving it. All right. Pie charts are for comparing parts. All right. They're percentages presented in the form of basically pie wedges. So it's intuitive. All right. I think the tendency nowadays is not to do an actual pie so much as a donut. All right. But it's the same principle. Right. I think the reason not to do pie so much and prefer a donut is because the wedges might be a little misleading, especially if it's pitched at an angle, which is something you can do. In other words, you tilt your pie in perspective, and it's sort of the perspective is misleading sometimes. I had done. The reason I say that is I had prepared a syllabus, and I was all proud of myself that I had made a pie chart to show how the grades were distributed, but in doing so, pitching it at an angle, it sort of misled my students. They looked at the wedge perspective rather than the number, right? And it wasn't incorrect, it just was, because it was at an angle, it just was little misleading. Anyhow, a pie chart or a donut, these types of charts are always a maximum of 100%, as would make sense. And any of the individual parts would be some percentage that is, when the wedges is smaller than 100%. All right. These are circle graphs. These are, again, bar charts of different types. All right. There is something else that you can do, right? And that's, well, there's two other things technically. But let me get this out of the way. In the case of histograms, right, the horizontal axis represents the categories or classes, really. All right, and the vertical axis represents frequency. This is very important, okay? Make sure that that is what, if you have to draw something like this for your own sake, make sure the vertical axis is the frequency axis. All right. Now, what you can do with a bar chart is translate it into something called a frequency polygon. All right. This is something that basically looks like a mountain range in profile. All right. And it's like if you have bars that look like this, essentially, kind of look like fingers, a frequency polygon is drawing basically on top of each of the peaks. So because it may occur, like so, all right, it looks something like a mountain if you look at it in profile. All right, a zigzagging line graph would be just basically the line, all right, not the inside portion of either the bars or what would be the mountain underneath it. No area region underneath it, just the tops basically connected, like connect the dots, on a placemat. Okay, that's just the next logical step. Okay, so let me go back for a moment. These again are just the tops. Just the top, peaks, shall we say, connected. Let me go back and make sure that there's some vocabulary sort of very firmly identified. It's getting a bit hot already. Take a little coffee here. And with that in mind, sorry I'm standing in the way, but I'm going to get back to this chart first, and then we'll do some examples. Let's get some words clarified. All right, we'll start with this. There's frequency, which is intuitively how often something occurs. On a histogram, this is essentially the height of the bars. A frequency distribution is that visible? Looks like it is actually the table to start with, listing items observed and their relative frequencies, or their corresponding frequencies. I'll get out of the way in a second. Just a side note, if you go into teaching, all right, write in capital letters. It's a little bit easier for kids to see from far away. I know I don't do that all the time, but I will try. All right. A frequency distribution is the table that you start with, listing items observed and their corresponding frequencies, right? You translate frequency distributions into histograms, right? Really. You'll hear this phrase thrown around a lot. I feel like this isn't gonna right, so let me figure out another one. A class. All right. Well, sometimes in other contexts it's called a bin. Is bin width. Essentially a number used to indicate how wide each section, shall we say, for lack of a better word, of the frequency distribution. Right. And just to make sure it should be consistent. Right. It doesn't change from one bar to the next or one item to the next, right? It's a number that is, it's the width essentially of each of the bars. Right, it's used to indicate how wide that category or class is. Okay. There's a formula for that, but we're going to come back to it anyway. Let me see if green is cooperative. Modal class. Is that visible? Barely. Okay. I'll read it if I have to. It is the class, that's better, we'll get to that. The class bin with the most data. Therefore, what it means is that it has greatest frequency. Just was a matter of colors here, I'm going to go back to blue. Class mark, which again is another formula you're going to see, essentially. The class marks are the midpoints of a class, bin, whatever you want to call it. This will be different for each, because it's a point. Lastly, and you already know this technically, but a histogram is essentially a bar chart without gaps. Translated frequency distribution. All right, you start with the table and you make bar charts. All right. Frequency distributions are technically the table. All right. All right. So let's do some examples now. And with that in mind, take a look at 2 pages. Where is it? Word problems, here we go. All right. As I mentioned, I swiped this from another textbook we have been using. But I like this because it's very good to introduce categorical bar charts first, to get a person's feet wet, and then get into frequency distributions. Okay. So what you have here is, let me get a little bit of light here. Down here, a data array, notice it's rectangular, of distinct categories of vitamins, vitamin C, vitamin A, vitamin B, and D. All right. A health food store recorded the type of vitamin pills 35 customers purchased during a one-day sale. All right. Each one of these is an individual customer simultaneously. This is a customer who purchased the vitamin C. On the same day, this is a customer who purchased vitamin A's. All right. Construct a categorical frequency distribution for this data. All right. What does that entail doing? Well, it's isolating what are the unique, distinct categories, and then, drawing them on a table like this. All right. What you don't have normally when you look at the examples in MyLab, there's no third middle column here. But if you're given the data array and you have to create the frequency distribution yourself, all right, I would add this third column and just make tally marks to keep track as you're doing it. All right, so let me show you two things simultaneously. I'm going to put this diagram I already showed you because it's the same information up on the top here, and we could have it side by side with the table underneath here. Stop that. Okay. All right. That's a little bit of a nuisance. Yeah, I might do. I might get crafty here. Do this. Yeah, this will suffice. All right, let's start by looking at the data array and identifying how many distinct categories there are. All right, in the array. All right. If you stare at this long enough, you go, well, there's A, so there's one category, B, C, and D, and E, so 5, all right? What you might do for the sake of organization is take this blank, all right, of a frequency distribution and make 5 rows. So I'm going to do that to set a good example here, all right? And I'll just go this far, at least initially. Every time that you do something like this from scratch, start with a blank, all right, and again, decide how many categories there are, and then make yourself some rows, all right? So, what are the names of the distinct categories? I'm going to make little bullet points now, all right? There is vitamin A as a category, vitamin B, nothing about B12 or B6 or what have you, C, D, and E. All right, now, here's kind of the fun part, all right? And it's really the reason why I'm telling you. When you have to translate a data array into an actual numerical value, which is the Hindu Arabic numeral, all right, do start with a tally mark, and it's very difficult to, I mean, it can be tricky sometimes if you have a very large array to miscount. It's very easy. So, and difficult to keep track. So the tallies will help you. Remember, when you make tally marks, it's intuitively 4, and then a slash is a 5th one, and you count by 5s. So train your eye to read left to right. All right. So we're gonna go in alphabetical order like this, and I'll use red to start with. And as you count, cross them out, so it'll get easier and easier as you proceed. All right, so first row is an A. So I'm gonna put an A here for a tally. Second row is an A. I'm gonna put a tally. Third row is an A. Fourth row, there's 2 A's, so that's 5. And then the 5th row here is an extra one. All right. So 6 it would seem total. I'm going to just wait to finish the rest of them now. Okay. Do the next one. B would be logical, right? Go back to the top here. Go across the row. No B's. All right. Second row, 1 B. Tally. Third row, no B's. Fourth row, 2 B's. 1, 2, well, not to be. And then a 5th row, 2 B's. So, coincidentally, 6. Next one. C. All right, so quite a few of these, right? 1, 2, 3, 4. So, 1, 2, 3, 4. And second row, 1. Third row, 1, 2, 3, 4 again. 1, 2, 3, 4. 5th row, 1, 2. 1, 2. 5th row, 1. All right. There seem to be 12. And then D. I'm going to do blue again because I'm running out of colors. D is 1, 2, 3, and that would seem to be it. You know what? I missed one. I missed 1A, which if you cross them out like this, it makes it more obvious that you missed one. You can just go back and fix that. So I'm going to just double check now with my A's, now that I finally caught wind of it. All right, 1, 2, 3, 4, 5. Looks like I did count it, 1, 2, 3, 4, 5. I just neglected to cross it out. It was a dodo mistake of mine. All right, let's see. And lastly, the E's. Shall I use black now? 1, 1, 2, 3. 1, 2, 3. 1, 1. 1, 2, 3. 1, 2, 3, and that looks like we're done. So now I'll just eclipse this because it's not necessary anymore. We've taken data array and we've translated it at least into tally marks. And I'll just be a good guy and I'll extend this line now. And now you just translate these tallies into an actual frequency. That is a Hindu-Arabic numeral. All right. So this would appear to be 6. All right. This would appear to be coincidentally 6. The C seems consumers are interested in C vitamin most of all, 12. And D, not so much. But vitamin E is 9. Right. Again, you don't have to include a tally mark system, but to me that's the most intuitive and somewhat satisfying method of going from here to here. Okay. All right. The actual frequency distribution is basically these 2 columns. All right, the category and the actual Arabic numerals listed for each category respectively. All let me show you something from the procedures that come from the textbook, because they're very helpful. And then we'll go back and do the next example here. All right. Take a look. I'm going to end up using a chart like this once again. But let me show you something here, because it's very helpful. Okay. I want to highlight some information from here. We're going to be doing a grouped frequency distribution next. All right. In this case, the classes should be the same width. Remember, this is what I was saying before. The class or bin width, all right, this should be consistent. All right. If it's not given to you, then you will make it consistent. All right. The classes should not overlap. They're right up against each other. No gaps. Okay. And each piece of data should belong to one of the classes, only one. All right, now what I really want you to highlight is this in here. All right, maybe take red or a highlighter. In addition, it is often suggested that a frequency distribution should be constructed with 5 to 12 classes. This is very important, all right? If there are too few, drop it, sorry. That's twice, okay, sorry. If there are too few, all right, or too many, all right, the distribution may become difficult to interpret. All right, for example, if you use fewer than 5 classes, you risk losing too much information, all right? It's not helpful. If you use more than 12, you may gain more detail, but you risk losing clarity, all right? Let the spread of the data be a guide to deciding the number of classes to use. But this is the range, basically, okay? You want to be in the 5 to 12 category. Okay. Now, if you look at this next example here, there's a second data array to illustrate grouped frequency distribution. All right, just pay attention to this for a moment. All right. In one math class, the data below represent the number of hours that each student spends on homework in an average week. All right. Construct a grouped frequency distribution for the data, and they're specifying 6 classes. All right. You'll see why they did that in a moment. All right. Left to your own devices, what I would suggest, at least to get your feet wet, to get going here, is to look for the lowest value, all right, and also look for the highest value. All right. But bearing in mind, you want somewhere between 5 categories and 12 total, all right? Now, if you stare at this, and unfortunately the sun is coming in, so I'm going to try to crop this to keep it from making a problem. And pull this up slightly more. Okay. If you stare at this, 0 does not occur in here, right? The low end of this would appear to be 1, all right, in this particular example. All right. And again, as you go through the array here, it would seem that the highest value, the number of hours that a student spends on homework in a week, is 18. All right. So, if judging by these numbers, all right, if they're saying use 6 classes, all right, this will decide ultimately pardon me, how wide the individual classes will be, right? And we care about that ultimately as well, because when we take the data array and try to translate it into a frequency, we're going to have to consider more than one number that happens to fit in each of those classes. So what I do a lot of times myself is at least start with subtracting, all right? And you would get 17 in this case. Now, if we're going to divide 17 by 6, it's not going to work out so well, right? It's going to be, 2 point something, right? So if you just instead rely on 18 and divide by 6, then you're going to have 3 numbers per class, basically, to look for when you're categorizing. All right? Now, what I'm going to try to do is I'm going to have this scooted up over into the corner again, and then I'm going to bring back the scaffold that I'm giving you for constructing a frequency table. All right? So I'm going to scoot this up as best I can, and if necessary, minimize it just a wee bit. All right, that looks like it's conducive. And get this back. All right, let me do this first. Here's our blank scaffold. If they're saying you must use 6, then you must use 6. So I'm going to make basically 6 rows here. Would be a category, a second category, a third, fourth, fifth, and a sixth one, right, ideally. The difference between the true category, categorical frequency distributions and the grouped one, which we're going to do now, is they're going to be ranges of values. So, you know what, I hate to say the word ranger because I don't want to confuse it with something else, you know. I'm not saying domain either. Intervals, if you will, intervals of values, all right, in place of what would be a category. So I'm going to put a hyphen here to get you rolling. Something to something. All right, now we're going to go back and look at this. All right, and we've already decided the minimum is 1 and the maximum is 18. And just because it makes the distribution nice and even, all right, rather than do a difference in this particular case, since they're suggesting 6, all right, taking the maximum of about a distance of 18. I know that the difference is not exactly the same. We're going to use a space of 3 values each category. All right, so what's the lowest number? The lowest number is 1. I wonder if that's sharp enough to see. Let me see if I expand that just a little bit. That's the whole array. That looks better. All right, let me just scoop this over here. Tighten that up just a little bit. There you go. All right. The lowest value is 1. So if there are 3 values each category, that would essentially be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and we would fit in exactly 6 categories. All right. All right. But again, we're not going to present them as a category so much as we're going to now present them as sort of a brief sort of spectrum or interval. So from what to what, right? From 1 to 3 is going to be our first essentially category here, class, right? From 4 to 6 is our second one. From 7 to 9 is our third. From 10 to 12 is our fourth. From 13 to 15, and from 16 to 17, 16 to 18. There you go. All right. Now, more or less, it's the exercise from earlier where you have to go through this, and just to spare yourself some trouble, I'll move this down here just for the moment. Well, there's really no place to work. Shoot. Just for the lack of space, what I'm going to do is I'm going to squeeze my tallies in here and here, just for these two categories, because I don't want to make it not sharp enough to see from far away. All right, those of you who have the actual copy, you can follow along. All right, so let's start from the first row here in the array and look for 1s, 2s, and 3s, and cross out 1s, 2s, and 3s as we go about the process. Now you can see there's a 1 here and a 2 here, so we have 2 tallies. Another 2, so we have 3. Next row, there's a 3, so that's 4 total here. Another 1, so that's 5 total here. Next row, there's a 2. And let's see. Next row, there's a 1 and a 2, so 1, 2. Crap. I'm just going to put it above here. 1, 2, 3, 4, 5, 6, 7, 8. Good. Third row here. 1, 2. So 1. There you go. All right. Next one, I'll use blue for the sake of distinction here. We're looking for things in the 4 to 6 range. All right. Go back to the top row here. There's a 6. There's another 6. There's a 5. Second row, there's a 4, and then a 5. So we have that. Then there's in this third row, 1, 2, 3, 4, 5, 6 of these. Wow. All right. 1, 2, 3, 4, 5, 6. And the the fourth row here, 1. And in the fifth row, 2 of them. All right. That's quite a lot. Okay. Reluctantly, I will use green. The whole point of crossing it out again is that it makes it a little bit easier to get through this the more as you proceed. Right? In the 7 to 9 range here, you have a 7, so there's 1, and a 9, so there's 2. Right? 1, 1, 1, 2, 1, 2, okay. 1, 2, 3, 4. 1, 2, 3, 4. Okay. In the 10 to 12 category, there's a 12, so 1. 1, 2, 2, 3, 4, 5. 3, 4, 5. And I think that's it. Okay. In the 13 to 15 range here, we'll go back to red. 1, 1, 2, 3, 1, 2, 3, and let's see, there's one more, so 5 there, and one more set of blues here. All right, lastly, 6 to 18, there's a 17 here, and an 18 here, and 16 and 18, so 2 of those. And looks like there's one more here, just not to confuse it with the tallies that are in the way. All right. So just 5 of those. Okay. Now, having gone through the array, looks like we've accounted for everything. Everything appears to be crossed out and or circled. So I'm going to be very careful and remove these so that I can get them out of the way of the rest of the diagram here. All right, so what do we got? To translate the rest of this, all right, into an Arabic numeral. In the 1 to 3 spectrum, it appears we have 10 as a frequency. In the 4 to 6, we have 5, 10, 14. That should be blue, but hey. Trying to be consistent here. Okay. In the 7 to 9, we have, looks like 10 again. 10 to 12, we have 6. And in 13 to 15, we have 5. And 16 to 18, we have 5 as well. Okay. Now, here's the fun part. All right. We're going to translate, again, the frequency distribution is technically these classes, all right, and these frequencies, all right, in tandem. All right. What we're going to do is we're going to kind of treat them as the x-axis on a diagram and the y-axis, sort of, you know, on a what would be a two-dimensional coordinate plane, you know, something like that. All right. Now, before I do that, I'm going to try to preserve the information over here just to kind of keep it out of the way of the projection that I need. So I'm going to say, I'm going to write in black now, all right, again, what is going to represent the x-axis parts, all right, and what will represent the y-axis parts here, all right. So, all right, x, y, 1, 2, 3, 4, 5, 6. All right. 1 to 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15, and 16 to 18. And the frequencies, relative frequencies here, are corresponding 10, 14, 10, 6, 5, and 5. I just need to preserve that much of this table. And now I can move on to something else that I want you to highlight. All right. Going back to this sheet for a moment, from procedures, take a look at this. Here's information about a histogram. A couple of things I want to emphasize here. As you can see in the example that is on this piece of paper, Here's the bar chart, and then there's a frequency polygon superimposed upon it, as would often be the case. All right. What is important? All right. A histogram is a graph with observed values on a horizontal scale. All right. All right. So the horizontal scale are the observed categories, classes, etc. Right? Values. They're basically intervals. I hope that that's visible, and if it's not, I will rewrite it. The horizontal scale, my right is getting weak here, are intervals values. Right? The frequency classes, the frequencies are on the vertical scale. The corresponding frequencies, as previously stated, but just to reinforce. It's good to, especially if you're a teacher, repeat yourself a lot, all right? Especially when something is very novel, as this probably is to most people. Never get mad at somebody asking you a question, all right? A bar is constructed above each value. The last one is used to indicate frequency of value. Okay, this is important, all right? The horizontal scale need not start at 0. All right, however, and the calibrations on the horizontal and vertical scale do not have to be the same. Okay. The vertical scale, on the other hand, must start at 0. Okay. It may be necessary to break the vertical scale. What that means is this. Sometimes when you see a graph like this, just because the data starts so much further up from 0, the way that they will illustrate that there's a span between where the very bottom is 0 and wherever that you are looking, all right, they will draw a little squiggle like this to indicate that there's a break, all right? It may be necessary to break the vertical scale, as was done in displaying stock B, whether this was a different picture, all right, on page 729, to accommodate large frequencies. Okay, all right, so just beware of that. The horizontal scale doesn't have to start at 0, but the vertical scale does, all right? As for the scales themselves, they don't have to be calibrated the same. Okay, which means that, in other words, the increments that you have here do not have to be identical increments that you have this way. Okay? Now, let me go back to this, and I'll show you how you would draw this from scratch. I need to back this off just a little bit. As you can see, it's a little too small, I feel, but it's not going to let me do this too much. I'll leave it like that. All right. We're going to take this information from earlier, the last example, and now translate it into a histogram. Brute force. All right? Why? Because at least brute force is intuitive. Right? It may be tedious and it may take a lot of time, is what I mean. But it'll give you a feel for it if you do it by hand. So rather than just simply allowing the calculator to do it for you. Okay? So here's what I'll have you do. remember, the vertical axis, this is the vertical scale, right, represents frequency, right? And what is essentially the horizontal scale here represents the classes intervals. All right. Now, this is going to start at 0 vertically. This can if you want to, but it doesn't have to. What I would recommend you doing, right, especially because we're going to do a frequency polygon in a moment, is leave a blank here. Leave a space on either end. The two extremes. Okay. Now, it's a little different from traditional two-dimensional graphing. These are not really coordinates, they are intervals, as you can see. But what I'm going to have you do is label the bottom of the second column, label the bottom of the third, the fourth, and get to the end. So label these 1 to 3. Just under here. You can put them in a little capsule here. 4 to 6, 7 to 9, 10 to 12, 13 to 14, 13 to 15, and 16 to 18. And again, there's an empty space here on purpose, and there's an empty space here on purpose, all right? Now, in the 1 to 3 interval, we observed a frequency of 10. What you would do is work with graph paper so that you have an even increment, right? It's not just, don't do it by hand. It's easy to make a mess. Use line paper of some sort. This is why I gave you this blank, all right? And put an X, all right, to count 10 in this category. So one box is an X. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? That means that the top of this line is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The maximum was apparently 14, so you can increment up to there if you'd like. 11, 12, 13, 14. And that's dead 0. All right? Starts at 0 vertically. Remember that. All right. Next category, the 4 to 6 range is 14. So again, satisfying X 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's 14 X's tall, or boxes if you want to shade the entire box, but it's less work, right? In the 7 to 9 spectrum, all right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the 10 to 12 range, 6. 1, 2, 3, 4, 5, 6. It's fun, right? This is a 13, I swear. All right. 5, 1, 2, 3, 4, 5. And from 6 to 18, another 5. 1, 2, 3, 4, 5. All right. Now, this is beginning to come into resolution as a bar chart, but it's not quite yet, right? So what would you do to make it look more formal, right? Well, go to the tippy tops here and draw horizontal lines like this. Right? And then because you can see that they're pressed up against one another, just draw the lines down the verticals here. Right? And there you evidently have bars, right? This is, again, grouped, which implies that some stuff is in parentheses, right? Frequency, distribution, translated to a histogram, as it would be. A genuine histogram would not have gaps, right? That would be just an ordinary bar chart, all right? If you want, you could, to make it a little bit more distinct, this is up to you, draw some shading of some sort here, maybe opposing herringbone sort of style here, and making tweed, something like that, to make it look obvious that this is an entire bar, not just a skinny stack. That's up to you. Now, let me go backward for a moment, right, and discuss something else with you. You can, without doing a calculation, pretty much do the subsequent calculations, estimates, without doing any math, is what I'm getting at. So, but let me show you something, and then I'll come back to this. All right. This is on the procedures page, but I want to bring this up now that I can. All right. As you can see, once you have a frequency polygon or what have you, a histogram rather, you could establish the frequency polygon by taking these two things into consideration. Now, I don't want to erase anything really, so I'm reluctantly going to remove just a little bit. Around the edges. All right. There's two things that you would need, and if you're going to superimpose, again, a frequency polygon is more or less that mountain range and profile that is superimposed on your histogram. All right. It is helpful to consider these two things, the class width and the class mark. All right. The class width, again, is the consistent width of each bar of the histogram. You could figure it out just by staring at the example that you have, but to generalize, there's a formula here, all right, which I'm going to move just out of the way of the middle finger here, all right. You could calculate the class width by subtracting the second class lower limit and the first class lower limit, all right. Now, we know what they are here, all right, but just bear in mind, these class widths consistent. So you only have to do this once. Right? So you could just do the first two to, take numbers from the first two here to do this calculation. All right? The class mark, you want to establish the first one, and then you can employ this class width in tandem to get the subsequent ones. I'll show you what I mean by that in a minute. But here's the generalization. It's the first class lower limit, I just abbreviated here, plus the first class upper limit. So you're just looking at one bar, all right? And taking an average more or less, you're dividing by 2 to get the middle exactly, okay? So bear that in mind, all right? The class mark is the midpoint. And this will be different for each bar. Okay. Now, going back to this scaffolding here, where is it? There we go. Moved. Shoot. This is why I didn't want to move it at all. There you go, that's better. Okay. Here we have, again, our frequencies. Alright, 14 is up here. Alright, 0 is down here. This is 0. You could guess, again, that what it would be exactly in between 1 and 3, it would be 2. But if we use the formula, right, which is a good exercise because you have other problems that are more complicated than just these numbers, we'll calculate the class width. Right? So, It's the second lower limit minus the first lower limit, right? The second lower limit is 4, right? Minus the first lower limit is 1, all right? What's 4 minus 1? 3 wide, which we already knew anyhow from the other work, but this is validating that point, and we're going to need this number momentarily. Right? If we want to calculate the class mark, which again is essentially the midpoints here, we know that in the case of this first one, it would definitely be 2, but let's validate that. All right? If the formula holds true, and it is, it's the first lower limit plus the first upper limit divided by 2. It's an average essentially of those two things. So, what is the first lower limit? 1 plus, what's the first upper limit? The other end of the spectrum here, 3. What is 1 plus 3? Add first, and then divide by 2. Right. Well, 1 plus 3 is 4, and 4 divided by 2 is 2 is the midpoint, right? Otherwise known as the class mark, but of this individual bar. So if you can figure that this is 1 and this is 3, right smack in the middle would be 2. What you want to do when you're constructing a frequency polygon is go to the dead middle here, dead center here, and then put a dot like a cherry on the cake right at the tippy top of this, right? Again, you can pretty much get away with doing that again here, and here, and here, and here. But let me put the cherries first here, and then show you how you can calculate without the picture, because sometimes you don't have the picture, right? What does that entail doing? Right? It means taking this consideration, if you wanted to figure out what the number should be here, at the bottom, here, and here in this horizontal scale. You're going to take the 3 wide, which would be true even between the midpoints, all right? And you're going to take 2 plus 3, and you're going to get the next midpoint. This is the subsequent midpoints. Hopefully it's not too messy, right? It would be the first midpoint plus 3, right? The next one would be 3 ahead of that, all right? So what's 2 plus 3? 5. Then you're going to do 5 plus 3. Right? It's going to be consistently that width apart. All right? But the actual value is different. 5 plus 3 is 8. Right? Halfway between 4 and 6 would naturally be 5. Right? Halfway between 7 and 9 would be naturally 8. Right? 8 on the horizontal scale. All right? Keep doing that until you go to the end. All right? 8 plus 3. Plus 3, plus 3, all right, is 11. All right, switching back and forth is a bit of a nuisance. 11 plus 3 is 14. All right. 14 plus 3 is naturally 17. All right. So again, halfway between 10 and 12, you intuitively would know is 11, right? But use this formula when you're not sure. If you don't have a picture, you can calculate it. All right. Between 13 and 15 is 14. Between 16 and 18 is 17. Would be the middle. Okay. Now, we need to get the mountain range connected in here by connecting the peaks. All right. And in order to do that, we have to bring, this is the reason why I left a blank space here and a blank space up in the front. All right. You could just simply draw a dot on the horizontal axis right here, right smack in the middle, the lowest cherry ever, right? And the same thing here. But if you wanted to calculate it, it would be, in theory, 17 plus 3 would be, if you had data in that, in a subsequent category, it would be what? It would be 20, technically. Right. Which means that this would be 19 to 21. Right. Back here, technically, it would be negative, right? It would be 0, -1, -2, So 1 minus 3 in this instance would technically be -2. Pardon me. 2 minus 3 would be -1 is the midpoint. You don't really have to calculate it, all right? But it would technically be, if this is 1, the middle would be 0, and then the other extreme would be -1. All right. Anyhow, if we're constructing a frequency polygon, again, just to go back to this to reinforce the concept. All right. All right. It is helpful to calculate the class width and the class mark. Right. We got the width. We already knew it was 3 anyway, but we calculated it to validate. All right. And we could have figured out what the midpoints were, just sort of intuitively, but we validated that. Right. And we projected and extrapolated forward and extrapolated backward, technically. All right. Now it's just a matter of basically connecting the dots to make a frequency polygon. It's kind of fun, actually. So hopefully I didn't move that too much. Put this back. Looks like it's okay. All right. And I'm going to take out a ruler and connect the cherries. Hopefully this green will cooperate. Bit of a jerk. Let's see. There you go. Down to the axis, and then technically at an angle this way, and then technically at an angle this way. Come on. And then this way. T-square's getting in trouble. And these two. No. Don't break the acrylic. And this is a flat line, because it doesn't change from here to here, in terms of frequency anyhow. And then you go down to 0 again. Now, to make it a little bit more satisfying, what I'll do is I'll remove the histogram from behind it. Now, so long as you have it down to the zeros here, all right, and you have all the peaks connected, this is your frequency polygon. If you wanted to take it one step further, all right, which would be, usually shaded in here like this. Green kind of sucks as a marker, unfortunately. But I'm trying my best here. Right. A shaded in region. No problem. Let's not do that. Okay. Is a true frequency polygon. Okay. Again, it looks something like a mountain range superimposed upon the histogram. A zigzagging line would be just a line graph. Right? It's not shaded then. enough of that. Moving on. Let's consider a stem and leaf plot. Yeah, look at this procedures again, and I'll emphasize some information. Here's those same formulas if you prefer. Alright, the next thing we're going to do is a stem and leaf plot. Diagram. Green doesn't write, but it does take forever to get rid of it. Alright. A couple of things to emphasize. A stem and leaf display is a tool that organizes and groups the data while allowing you to see the actual values. Right? It's more or less a sideways histogram. Right? They just don't bother to draw bars around it. Right? The group left of the digits, the left group of digits is called the stem. Right? Alright, this is basically the usually the tens place, something like that, or the hundreds if you have 2 digits. Alright, the remaining group of digits to the right is called the leaf. Right, this is usually the ones place. In theory, it could be a decimal. Right, ones or lower. Alright, there is no rule for the number of digits to be included in the stem. Right. Usually the units digit is the leaf and the remaining digits are the stem. For example, the number 53 would be broken up into 5 and 3, and 5 would be the stem and 3 would be the leaf. The number 417 would be broken up into 41 and 70. There's 2 digits in the stem and 1 digit in the leaf. Right. If you had a number like 6, you could make it 06, like on a jersey. Okay. Now, as an example to illustrate this style of graphing or displaying information, let's look at this swiped again from another book, because I liked it. We have another data array. And this one is much shorter. What is it? Okay. It's no secret that gas prices have fluctuated wildly in the last few years. Right? Perhaps remember when you were a kid in the early 20-aughts, between 2000 and say 2010. Gas prices were quite terrible then. But between 1980 and 1999, they were surprisingly stable. All right? According to the Energy Information Administration, which sounds totally made up, the data array below represents the average price in cents. So this is really $1.19, but it's written in the style of pennies, so 119 cents. All right, per regular gallon of unleaded gas over those years. All right. If you go back to 1980, between 80 and 90, there used to be leaded gas. In fact, and that's funny because they used to refer to leaded gas as regular. All right, but it was just not something you want to breathe. Anyhow, draw a stem and leaf plot of the data. I'm going to try to move this up and again put the scaffolding that is useful adjacent. So let me get this out of the way. And here is a stem and leaf diagram that I prepped for this. All right, I'm going to have to, unfortunately, back this off a little bit to show you how I'm going to break this up. All right. If you stare at the array unique to this problem, all right, let's break, if this leaves are going to be essentially the ones place, if you think of these 3 digits as being hundreds, tens, ones place, all right, then we'll make those the last digit, all right, they'll be the leaves. And what would be the tens and hundreds place will fit into the stem. Right? We'll decide based upon that how many categories essentially we'll have here. All right. If you look for the lowest number appears to be in the 80s. All right. And if you look at the highest number, it appears to be in 130. All right. So let's start. I'll just put this over here. It's going to get me in trouble. All right. We'll decide how many stems there are if we count by tens, essentially. All right. There's going to be 80s and 90s and 100 and 110s and 120s, therefore, and up to 130 category. So 1, 2, 3, 4, 5, 6 again. All right. Now I'm going to try to expand this without making it difficult to see the whole of it. Not that. This. And I'll scoop that up so that you get to see everything. And then put the array back. Alright. Shoot. That looks like it will fit. Okay. So, remember, the tens and the hundreds place essentially are going to be on this side of the solid line, and anything that fits in the 80, essentially between 80 and 89, inclusive, would fit over here as a digit. Right? So this is going to be 8 for 80, 9 for 90, 10 for the hundreds, the early aughts, if you will, and then 11, or what looks like 11 for the 100 teens, then the 120s, and then the 130s. And similar to before, we're going to read across this back and forth a number of times, all right, to fill in these increments here. Now, I would recommend doing this on graph paper of some sort, because you want a consistency in the width of these columns, all right? Because you're going to be comparing, how tall they are, but just sideways, right? Anyhow, if you read from right to left, both lines here in the array, you can figure out what would be fitted into here. The only tricky part to this, and you're not really required to, is trying to put in numerical order. You may have to do it more than once. It's not required, but it's better organization. Try to put in numerical order, just try to, all right? If you go through this first line, you see that there's just one thing that's in the 80 category. If you go through the second line, there's nothing. So the only thing that would be fitting in here is just this single 6-digit in this first column, all right? Now we'll do the 90s, right? Having done that, I'll cross that out, right? Read across here, you see that there are two 90s, so I'm going to put a 0 and then a second 0 to represent these two, right? And then I'll look in the next category here, there's nothing else for the 90s, all right? Now when you get to the 100s, right, that's the things that are between 100 and 109, essentially. There might be a lot, or maybe not. Well, there's two. All right. Reading from left to right, there's 100, so 0 would go first. All right. And there's 106 is the only other one, so that wasn't so bad. All right. In the 110s, that would be from 110 to 119. All right. Now we might get into a little bit of trouble, so we have to be a little bit more strategic again. If you're going to try to put these in numerical order, you're not obligated to, but it would be cool. All right. Let's look for something that is exactly 110 first, because that would be 0, right? Nothing that is 110. I did forget to cross that out. But there are, it appears to be, two 111s. All right, so I'm going to put a 1 here and then a second 1 here to represent 111 and 111 cents, meaning $1.11. Alright, having accounted for that, what comes after one digit? 2. So we'll look for 112s. Back here again, There is one example of 112, so I'm going to slip a 2 in here. And check the next one, no more 112s. Next digit would in theory be 3, so 113. There's a 113, so I'm going to stick a 3 in here. And there's a second 113. So I'm going to put another 3 in here. And that appears to be it as far as 113 is concerned. All right, next digit would technically be 114. If you read across, nothing for 114 except to the second row. All right, so there's a 114, so we put a 4 in here. And that's it. Next would be 115. Back to the top. 115, it'd be a 5 in here. And then a second 15. There's another 5. All right. What about 116? There's no 116s. What about 117? Not in the first, but there is one in the second. So I'm going to put a 7 here. All right. And again, as you go along, cross them out because it'll make it easy for you to read it. All right. No 118s, but the next one logically would be 119. So that is the end of the spectrum here. All right. As you can see, I very strategically made this ahead of time. All right. But again, if you use graph paper, all right, you won't get into trouble. All right. Graph paper is a godsend. It really is. All right. Encourage your students. Give them the resource. You know, make them the papers they need. All right. Now, clearly, as you can see so far, all right, where is most of the data? All right. It's in the 110s range. All right. At least so far. We'll check the rest of it. All right. Things that are in the 120s category. All right. Back at the top, there's nothing 0. All right. So no 0 here. There's no 121, but there is a 122. So you'd have a 2 here. And there are 3 123s. So a 3, a 3, and a 3. Okay, and that's it for the 120s, it looks like. There's only one thing in the 130 category, and it's 131 itself. All right, and this is the whole kit and caboodle. Now, the beauty of this, again, is that if you take the time to strategically put things in numerical order, all right, there's a couple of things you can tell. Well, firstly, the stem and leaf diagram tells you, preserves, this is the end of this one, okay. It preserves view of the data, the actual numerical values. I hope that's not too faint, it's a little too hot, right? And I hate sucky markers, you know, that's the worst of that. It preserves a view of the data, the actual numerical values, and it tells you the modal class, the class with the most data. It would be this one, evidently, because that is the one that is a huge pile, it's just vertical. Pardon me, it's just horizontal. If you think about it as a bar chart, no one would ask you to do this, but I'm going to draw horizontal bars just to illustrate. This is something like a sideways histogram. All right, you can tell by the height of this, the width of it, technically the length of it, that this is the modal class right there. Right? Now, as a side note, if you wanted to get the true mode, that is the number that repeats the most often, what number is it? It's the number that you see the digit repeated in the greatest amount. All right? It would apparently be, I'm writing on myself again. I wish I wouldn't do that. It would be 123, apparently. That's the actual mode. All right, why? Because there's 3 3s here. All right, closest would be in this category the modal class, where the most data is. Most data per class. And this is the number that repeats most often. Okay. Alright, that's kind of neat, right? Again, it's something like a sideways histogram if you make bars around it. It just lets you see the actual values. So that's kind of cool. All right. Use this scaffold if you find it conducive. All right. Okay. All right. The last thing is the pie chart. What is it? It's not quite 10. What I want to do is show you how to make a pie chart. And if you want, you're welcome to use this blank table that I have prepared here. All right, this is basically the process if you had to do it from scratch. I think it's a very fun activity for your students. All right, and what I would do is basically get them in the habit of forming a survey question. What I did a long time ago, because it to me seemed to be the thing that unites us culturally Americans, right? Is what's your favorite movie, or category of movie. So here's some blank spaces to put in, maybe 5 categories. All right. The way I did it was something like this. I'm going to show you the results in a moment, but I want to walk you through the process. All right. This is a survey scaffold you could use. All right. Favorite genre of film or movie. All right. What occurred to me is that, okay, if I'm just going to limit it to 5 categories here, I'm going to have to group some. So what I did was, I hope this is better now. I said, all right, let's make this A as an action adventure films. And B, let's make this, I know there's going to be some overlap, of course, but let's call this sci-fi fantasy category. C, we'll make horror and thriller. I'll tell you what my reason is for this in a moment. Thriller. D for drama. That makes sense, right? Or maybe biographies, because life is quite dramatic. And C, we'd make a comedy. E, we'll make comedies. Or perhaps animated. All right. I really would like animated to be a separate category, but just for argument's sake, let's put these together. Because at least historically, cartoons are funny. They don't have to be. Animes are not always funny. Sometimes they're quite serious and elegant. But just to get through 5 of them. All right. My logic is this. What makes an action film? And you would tell the kids too. All right, or whoever's filling out the survey. What makes an action film? Explosions, right? All right. What makes an adventure film? Something like you're hunting for a treasure, or you're going on some kind of a journey. This is a person in the current, time frame. What makes a science fiction film? All right. Well, it's usually based upon science, so it could be anything that is scientific, say geology, even a story of rocks. But like, dinosaurs, or, space films, or if you're talking about fantasy, something that has wizards in it. A horror film, I make this distinction between a horror film and a thriller. As Alfred Hitchcock once said, what makes something scary is not what you see so much as what you don't see. Because, the movies that he made, they were not gory, they were psychological. So like what's more frightening oftentimes is what you're not sure of. Your mind will lead you into will talk you into being scared. It'll contrive something even if it isn't really there. All right. Horror films are gory, blood and guts, Texas Chainsaw Massacre. Thrillers are more psychological, again, not what you see, what you don't see. All right. Dramas, again, are, serious films, could be romance. And biographies I would put in there too, because it's simulating somebody's life, or discussing somebody's life, hopefully, truthfully. And comedies, again, are funny, naturally, and cartoons are historically humorous. All right, now, I, in spring of 2017, first contrived this. Well, no, I might have done it longer than that, but at least at Middlesex was the first time that I did it. And these were the results. I told them ahead of time, my students, I said, listen, these are your choices, all right? You can only vote once, all right? And then I said, show of hands, people who favor this overall, and then took a tally of it, all right? So this is the way it worked out, all right? 3 people, all right, liked action adventure, all right? 3 people were interested in sci-fi as a favorite category. All right, and to my surprise, all right, 8 people, all right, out of the group, the clear majority, as you'll see, were liked horror films, all right, to each his own, right? Drama, only 2, and comedies, at least the way I've defined these things, just 4. All right. Now, how would you translate these votes essentially into a pie chart? That's the subsequent steps. Again, this is a brute force way of doing it, which I would make a student do the first time because they'll enjoy it, all right, and it will maybe resolve some issues that they have with basic arithmetic in the process. Why? Because they finally have a use for this junk. All right, you're going to form a fraction, a ratio, to be more general, which is the frequency tally over the sum of the frequencies, which is essentially the totals here. So how many people voted in this case? The totals would be down here. You count them. 3 and 3 is 6. 6 and 4 is 10. And then another 10. So it's 20 people total. All right. So as a fraction ratio, all right, this would be 3 out of 20. And this would be coincidentally 3 out of 20. And this would be 8 out of 20, and 2 out of 20, and 4 out of 20. And as to be expected, if you added them all up, it should be one whole, so the total would be 20 out of 20. Okay. Now, you could lower the terms of the fraction, and perhaps you've been batted as a kid, and your instinct is to do that automatically. There's nothing wrong with that. But these numbers that you see here, 20 people total, are going to be, happens to be convenient numbers. So resist the temptation just yet. When you're trying to translate something maybe to a decimal or percentage, you sometimes want the thing that you have, all right, 20 here. Now, let's start with the decimals first. If you're going to convert a fraction essentially to a decimal, this is the process. Divide the numerator by the denominator. So 3 divided by 20. All right, is the most brute force way of doing it. And in which case, what do you get? You get 0.15 essentially. Hopefully that's visible. All right, it did the same figure here, 0.15. There's other techniques, of course, but if you divide, again, this will work 100% of the time, divide top by bottom. All right, 8 over 20 is 0.4. 2 over 20 is 0.1. 0, and 4 over 20 is 0.2. Okay. Now, the reason it might be convenient for you to convert to a decimal first, not always, is that it will make converting to a percentage that much easier. And again, you want percentages because they're palatable to the general public. Virtually everybody's okay when you say, well, it's 50% of people. They understand that, all right? That the maximum, the ceiling is 100%, and that anything lower than that is just a chunk of it, some portion. When you multiply a decimal times 100, what is that? The effect of that? It just moves the decimal point over twice, right? In each case, right? Times 100, times 100, times 100. So again, you can go directly from a fraction to a percentage, same way, times 100, right? But this is just doing it, trying to illustrate how you could do this. So this is essentially 15%, all right? And this is 15%. And this is 40%. And this is 10%. And this is 20%. All right? Again, the totals down here must, just to kind of validate your suspicions and give you a little bit more confidence perhaps, is if you add up all of these decimals, what should be the maximum when you add them? 1.00, one whole, right? When you add up all the percentages, what should be the maximum? 15 and 15 is 30, 30 and 40 is 70, 70 and 10 is 80, 80 and 20 is 100%. You're not going past 100%. And the last thing is to actually draw the pi wedges, right? How do you do that? Well, you'd have to translate from either your decimal or your fraction, if the denominator is conducive. In this case it would be. You're going to translate this to degrees. If you have a protractor, all right, you would measure, in theory, in degrees by multiplying by 360, all right? If you use 0.15 because you have a calculator, all right, times 360, here's what you'd get. This would become 54 degrees. And then coincidentally the same thing. And I'm not that boring, am I? All right. 0.4 times 360 would be 144 degrees. All right. 0.10 times 360 is 36, naturally. And 0.2 times 360 is 72 degrees. Again, to validate, right? If you added all these together, what would you get? Well, a circle completely, just arbitrarily, happens to be 360 degrees. Thank you, Babylonians. All right, Sumerians actually. All right, but again, 20 people voted, so the maximum was 20 out of 20. One whole, 100%, 360, just because that's what the Sumerians decided. Okay. It's this figure or these individuals that you would physically measure with your protractor as you proceed around a circle. Right. Now, to be fair, what most people would do is maybe use an Excel spreadsheet. So they would take this information, they would maybe draw the same table in Excel, but just more or less as labels. And then when they finally got it down to maybe these decimals, maybe these fractions, have the Excel software do this calculation for you. So if you'd like, here, let me just show you. Here's an old spreadsheet that takes this information into account. You could use this if you'd like. It's a little stupid right now, forgive me. Loading, yep, okay. I'll take a sip. Alright, it's a bit far away, but here's Excel, which is a very good program. See if I can zoom in on this. No, I don't want to do that. I've taken the same information, essentially, that I've just written here from my worksheet. And you would go into Excel and use the boxes, the cells of Excel, and fill in the information. Now, there's a couple of things. That's very far away. Can't see that. Oh boy. No, I don't want to do that. That's better. Okay. There's two things. Every one of these cells in Excel, if you're not familiar, is a glorified calculator. Right? You know how when you use a regular calculator, you basically press 5 times 2 or whatever you're doing, right? And then you hit equals last. Right? In theory, not that people do it this way, but if you wanted to, you can get any one of these individual cells to behave like a calculator unto themselves. All right? You would just hit equals first. So if you did, instead of doing 5 times 2 and then press equals on your calculator and it spits out 10, you would hit equals first and then put 5 times 2, which is an asterisk, and then 2. And then once you press enter, it spits out this in place of that. All right? if you don't use it that way, all right, you might use it to build a table like this, all right? And you would just, you know, when you write in regular words, they're just labels, all right? It's only translates into more or less a calculator if you put an equals in first, all right? This is really what you would start with, what's in red here, all right? I'll get rid of this and show you. I did the hard part here, you know, already with you. But if you wanted it to basically draw a pie chart, you really don't need that much information. I believe you could just get away with just highlighting what is in red here and then go up to the category where it says home and choose from the options. So let me go here and show you. It's obscured right now. Yeah, I don't want to update my office, thank you. There you go, insert. If you look over here in the options, you'll see some different types of charts, right? Here's a pie graph, for example. So, if you highlight what is in red, which is the left click and then drag down here, you don't have to do the 20, sorry. That's the tallies as an Hindu-Arabic numeral, and then go up to your choices here, and you could choose one in perspective, which is nice, or the donut, which is probably more common nowadays, or just the standard pie chart. It automatically divvies this all up. Now, granted, it doesn't say the information, all right, that it would be nice, but you could modify it, right? The width of this from here to here in terms of degrees is 144 degrees, right? The ones that are the same, which I would say is probably these two, those are the 45 and 45 degrees, right? This is the 72, right? And this would be the skinny one of 36, all right? What you can do, all you have to do is just type in, make a heading because it makes it easier for anyone else to read, but the tallies, all right, from the survey, all right, and then it will produce the graph, right? Now, I like to do things the old-fashioned way, and if you were going to do it, all right, again, you'd get a protractor, and you would line it up with 0, like so. I'd say this is 0 here, and this is 180. And you could read the edge here and see, yeah, that's exactly 144 degrees. Isn't that cool? Yeah, that's neat, I think. And then you would rotate your circle if you had drawn with compass, and you'd measure out the next amount, right? And you could put it in any, arrangement. It just chose this somewhat randomly where to put the pie wedges, right? And then you could change, if you want to, you could change the title. Let me just go back and show you very quickly. It's a little bit hard to see. Shoot. Again. If you click on the pie, all right, and you edit this, all right, right-click it, format labels here. You could get it to specify what the number of degrees are. It's a little bit hard to see still. Say this is 54, obviously. All right. You can get it to include the percentages in here. You could add a label for the genre. All right. You just play with it and trust yourself. Trust your own self-efficacy that if you just play with it, you'll have fun. All right, and you could decorate it. Right, and that's just making the standard flat type. I mean, look, if you really wanted to get crafty, all right, let me do the same thing here. You could do, the one in perspective. And that's cool, right? And what's even more fun about that is that, again, if you play with the settings of it, right, left click, click on the individual portions of this. You could spread apart the wedges, right? You could pitch the angle, you could rotate the whole thing, right? See? Isn't that neat? And that decorates, a report. It makes something appealing, right? I don't like, as a person who's a math person, right? I don't like nonsense, being sold something. But when it comes to math, math is not sexy, all right? And that's why people, especially little kids, they're scared of it. I mean, it's not to be sexy with children, but I mean, you know, it's unappealing to the public because they consider it inhuman somehow, right? So you have to sort of make things warm and fuzzy somehow, all right? Especially, and statistics is the way you do that. Again, it's the marriage of an art and a science, all right? To some degree, you know, especially, I'm talking about adults really, right? You have to make it seem more human, right? It's not appealing enough, right? Diagrams make things more appealing, i.e. it makes things somewhat sexy, all right? Figuratively speaking, all right? Anyhow, don't save. You could use that. Here's the same information. I made it as a PDF, all right? And that's that. Now, the very last thing I want to show you is again from the procedures, and then I'll stop. All right. If you go down here for pie charts, all right, if you wanted to determine the number of respondents in a category, it's just a matter of, in this case, it's kind of working backwards. If it's 38% of 800 people, all right, and remember, in order to utilize the percentage, you either have to have it in its fraction style, 38 out of 100, 26 out of 100, 17 out of 100, or use the decimal equivalent. Anyhow, you're going to be multiplying by the number of people in the survey, all right, and that will give you the number of people per category. All right, that's more or less working from somebody else's information rather than creating your own. Okay, it's going backwards for our purposes. All right. All right. That's enough of that. So let me turn this off and bid you adieu for the evening. I'm dying of heat. All right. For homework, do section 12.2 in my lab, right? It's not so scary, right? The more you do it, the more familiar it will be. A lot of the problems in this section is, again, making a frequency distribution, and all they want you to do is make a table, all right? All right? And then when you actually comes to histograms, you don't have to draw them from scratch, although it would be good to have that skill, which is why I walked you through it. All right? Be able to recognize the appropriate histogram. Okay? Thank you guys for sticking with me. I will see you again tomorrow. Be careful out there.